clear? Yes, the class has started. We have got 7 waiting and 7 likes. Hello. There was a mistake. There was a glitch. Some technical glitch was there. Now it is okay. Some internet issue. Again, kabhi kabhi ho jata hai internet issue. Sorry. So let's get along with chemical equilibrium, the degree of dissociation, and that's a very important part. We have already started with chemical equilibrium, and in between we have finished off with chemical bonding. And we have also done the NCERT reading of chemical bonding. We have also done the questions of chemical bonding. We have done everything about the chemical bonding. So now you can even do the NCERT questions of chemical bonding. Okay, that's what you are supposed to do. Now, once we have talked about the chemical bonding, now we are going to get along with chemical equilibrium back again. And in this case, we are going to talk about, okay, we have done the Lee-Chatelain principle. We have done the effect of the increase in concentration. We have done the effect of decrease in concentration, increase in pressure, decrease in pressure. Now we have to start over with the effect of the inert gas. That if we add the inert gas into a reaction, what it does. Okay. So here we have the Elixir dropper batch, which is going to start from 16th August, and you are going to use the code AVLIVE. So use the code AVLIVE for the Elixir dropper batch, starting from 16th of August. In-depth analysis of PYQ, revision classes, exam strategies, mentor-mentee program, mind maps. So anything you can expect for, wish for, it is there. And now our entire thing is complete. We have the botany, chemistry, zoology, and physics. Botany timings are going to be from 6:30 to 7:30 p.m. with Swati ma'am. 7:30 to 9 p.m. is going to be with me, that is Anoop Vashishtha. 9 p.m. to 10 p.m. would be Dr. Sachin Kapur. And from 12 afternoon to 1:30 p.m. would be Archana ma'am taking physics. So you have the classes completely filled with you. Okay. So here we have botany, and this is the YouTube schedule where botany would be taught by Swati Batra ma'am. 3 p.m. is going to be zoology by Dr. Sachin Kapur. 4 p.m. is going to be chemistry by Anoop Vashishtha. And 9:30 p.m. would be physics by Archana Pandey ma'am. And this is about me. That is what I am. And now this is Elixir dropper batch. And at this moment, you are getting exceptional offers by using the code AVLIVE, and you are getting the discount, additional discount of 4,000 rupees. So go ahead and use the code AVLIVE to get the additional discount of 4,000 rupees, and this course is available on the Unacademy store. Unacademy store. Is that okay? So this is what we have as Elixir dropper. Live ended? No, Mayuk Gupta. Mayuk Sen Gupta, live is working. Ask Mayuk to refresh. Okay, now let's talk about the effect of noble gas, or you may even call it inert gas. What is the effect of addition of inert gas? Now let's take an example. In this example, what we do is we have a closed system with a movable piston. Okay, this is a closed system with a movable piston. Now, in this movable piston, we have a reaction going on. Let us say any reaction could be there. Let us say we have a reaction of N2O4 gaseous in equilibrium with 2NO2 gaseous. This is the reaction which is going on. Okay. Now reaction is at equilibrium. At equilibrium, let us say the concentration of N2O4 is X, NO2 is Y. This reaction with this question we have already done. And now what we do is we block the piston here. We block the piston here. Now, once we have blocked the piston, and now what we do is we pump in here argon gas. The initial volume is V. Okay. When we pump in the argon gas, the final volume is again V because we do not allow the piston to move up. So initial volume is V, the final volume is V, and initial pressure is P. And what we do is we push in the argon in such a manner that the initial pressure increases, the pressure increases. The final pressure is equal to 2P. Fine. Understand it. This is the reaction going on in the container. The initial concentration or the equilibrium concentration are X and Y. X is the concentration of N2O4, Y is the concentration of NO2, and we push in argon gas in such a manner that the volume remains the same, but the pressure becomes doubled. Okay. Now the simple question is, in which direction will the reaction shift? Okay. Which direction will the reaction shift? Could you give me the answer? And I request you one very simple thing. Do not give the answer unless you calculate the value of Q. Check it out. What will be the value of Q and then give the answer. What will be the answer? Which direction will the equilibrium shift? And get the value of Q. So when we talk about K is equal to concentration of NO2 raised to power 2 divided by N2O4. And that is going to be Y square raised by X. So this is the value of K. Now, when we keep the piston blocked, that is, we do not allow the piston to shift. Okay. When we keep the piston blocked, then in that case, when we push in the argon gas in it, then in that case, the piston has not moved. Volume doesn't change. Now, the moles of N2O4 is X. The concentration again remains X. So when we talk about the Q, we talk about the concentration of NO2. Concentration of NO2 is not going to change because volume has not changed. And the concentration of N2O4 also will not change since the volume has not changed. And if the volume has not changed, the concentration of any of the reactant or product has not changed, the value of Q is equal to the value of K, and therefore reaction does not shift. Anyone has any confusion in it? Anyone has any confusion in it? No. Now, what does it mean? It means that if inert gas is pumped into a system at equilibrium, keeping volume constant, the equilibrium does not shift. The equilibrium does not shift. Is this clear? So there isn't any shift of equilibrium. Okay. Now, now let's talk about what will happen if the volume is allowed to change. Again, we have the container. Okay. And again, we have the piston. Okay. Okay. So here, now when we pump in argon, the volume increases. Let us say we say initial volume is equal to V, final volume is equal to 2V. Initial pressure is equal to P, final pressure is equal to again P. Now, when we talk about Q here, Q is going to become Y divided by 2 raised to power 2 divided by X by 2. Now, this becomes Y square by 4X. Now, the value of Q is less than K and the reaction shifts in the forward direction. That is towards more number of gaseous moles. The reaction shifts towards more number of gaseous moles. Any confusions here? Clear? So what we can see is that if inert gas is added to a reaction at equilibrium, keeping pressure constant, the reaction shifts to the direction which has more number of gaseous gaseous moles. Okay, so it is similar to effect of decreasing pressure. Clear? So the effect is not of pressure, effect is of the volume. So if the volume remains the same, then it doesn't make a difference whether the pressure increases or decreases. If the volume increases, then only the effect is going to be seen. Is this clear? So it is the effect of the volume and not pressure. Is this clear? So if we block the piston and make it immobile, this situation, the volume becomes a constant. Now, if we pump in argon gas, it is not specifically argon. It could be any inert gas which does not take part in the reaction. Argon is inert for all reaction. So here we can use argon. Argon में कोई ifs and buts नहीं रह जाते. इस condition में होगा, इसमें exception हो जाएगा. कोई exception नहीं है, इसलिए argon हमने लगा दिया. The gas is pumped so that the total pressure exerted by a mixture of all gases in the container is double the initial equilibrium pressure. Direction of the reaction shift. The condition is the statement relates shift of the reaction to the pressure which leads to a change in volume. Here what we have done is we have kept the volume constant. The pressure is increased, but the volume remains a constant. Here the number of moles of reactant or the products do not change. So the concentration also does not change. Now if I calculate the reaction quotient, as in the previous case, the ratio taken now will come out to be the same as the equilibrium constant, so the reaction will not shift. But if the inert gas is added to the system at equilibrium while keeping the pressure constant, if we keep the volume constant, the reaction does not shift. But if we keep the pressure constant, so that the volume double, हाँ मायूक helium use कर लो. Who says that? मैंने क्या कहा? It is an inert gas. Argon is cheap, easily available. It is the cheapest noble gas. Reason is simple, because it is 0.9% of the atmosphere. 0.9% of the atmosphere is argon, so argon becomes the cheap gas. So it is preferable that whenever we have the inert atmosphere, we will use argon. Is it clear, Mayuk? So we have to talk about not only just the chemical reaction, we also have to talk about the practicality and feasibility. Is this clear? Now, if the volume doubles, then in that case, the reaction is going to shift in the direction which has the maximum number of gaseous moles. Is it clear? Very, very clear. So don't ask me the question if we use helium. In this case, even you can even use nitrogen. You can even use oxygen, because oxygen is not also not going to react with it. So it is not a compulsion that you have to use argon, but any of the gas which is not going to react with any of the components in the system. You can use that gas, and that will be considered as what we say is inert gas. Absolutely clear, everybody? So please understand that whenever a reaction question is asked about the direction of the reaction under a given condition, do not answer before finding the reaction quotient. It's the reaction quotient which is going to decide whether the reaction goes in the forward direction or the backward direction. It's not your feeling. अरे ऐसा होना चाहिए, देखो ऐसा हो गया. यहीं पे सारा का सारा प्रॉब्लम आ जाती है कि आप अपनी फीलिंग से आंसर देने लगते हैं रादर देन गिविंग द आंसर बाय कैलकुलेशन। जिसने भी लाइक नहीं किया जल्दी से लाइक करो। ओके, नाउ व्हाट हैपेंस विद द टेम्परेचर? इफ यू इंक्रीज द टेम्परेचर द रेट ऑफ एवरी केमिकल रिएक्शन इंक्रीजेस। अब अगर हम इक्विलिब्रियम रिएक्शन की बात करते हैं, वन इज गोइंग टू बी एंडोथर्मिक, अदर वन इज गोइंग टू बी एक्सोथर्मिक। Okay, and one is going to be exothermic, other one is going to be endothermic. The increase in rate of endothermic reaction is by a larger factor. Reason? Endothermic reaction will have a higher activation energy. Okay, endothermic reaction, higher activation energy. ठीक है? So please understand that's what we have done in chemical kinetics. More is the activation energy, more is the effect of temperature. Clear? That is why the rate of endothermic reaction increases more. And when the rate of endothermic reaction increases more, that means the reaction is going to shift towards the endothermic direction, which could be forward or the backward. So if we find, okay, now when we talk about the equilibrium, equilibrium behaves like a very intelligent but naughty child who irritates you. He is going to follow your commands word by word, but is not going to allow you to disturb him. Equilibrium does not oppose you, but it resists the change. So equilibrium resists the change in one temperature. You provide heat to the system, reaction absorbs the heat so that the temperature remains the same. You remove the heat from the system, reaction generates the heat so that the reaction temperature remains the same. Okay, so react the system equilibrium will try to keep the temperature same. If you provide a lot of energy, then in that case the temperature is going to change. Okay, second, it tries to maintain the equilibrium constant, that is the ratio of concentration and partial pressures. You need to understand that we can change the concentration, we can change the partial pressure of individual components. But what it does is it tries to maintain the pressure, the ratio of the partial pressure and ratio of the concentration. That means it tries to maintain the equilibrium constant. Okay. So if you try to decrease the volume, it shifts to the direction which inherently has a lower volume. That is higher density. Okay. So the pressure is balanced. If you add the reactant, it consumes the reactant and forms the product. So the ratio does not change. If you add the product, the reaction shifts in the backward direction so that it consumes the product and forms the reactant. Again, the ratio remains the same. If heat is provided to the system, the reaction consumes it by moving to the endothermic direction. If you try to decrease the temperature, the reaction shifts to exothermic direction. Again, it tries to keep the temperature same. Okay, clear? So that's what we can see, effect of change in condition. So if a reaction is at equilibrium and it experiences a change in pressure, temperature, or concentration of products or reactants, the equilibrium shifts in the opposite direction to offset the change. That is, it absorbs the change. It is not going to, like you put the reactant in the reaction mixture, then in that case, it's not going to throw out the reactant. It's not going to say, nahi, mujhe reactant nahi chahiye. You add the reactant, it is going to consume the reactant and form the product. Okay, you add the product, it's going to consume the product and form the reactant. You add the temperature, you add the heat, it is going to consume the heat so that the temperature remains the same. You remove the heat, it is going to create the heat so that temperature remains the same. Clear? You increase the volume, it is going to increase the number of moles of the gases. You decrease the volume, it is going to consume the number of moles of the gases so that the pressure remains the same, but the density changes. Is it clear? So that is what we have as the equilibrium. So we have the statement like whenever stress or strain is applied to the system at equilibrium, the reaction shifts to nullify the effect. It does not oppose the stress or strain. It opposes the change. Okay, so that means it opposes the change. Is it clear? Now that is what we call as the Le-Chatelier's principle. Anybody has to ask anything here? Okay. Now let's see what are the different types of equilibrium constants. Okay. Now we can use different units of concentration. Clear? We can use molarity, we can use mole fraction, we can use partial pressure. These are the three generally used. Okay. We can use molarity, mole fraction, and partial pressures. Okay. When we use molarity, we call it Kc. When we are at mole fraction, we use Kx or Kchi. When we take partial pressure, we call it Kp. Okay. Even if the values are going to be dimensionless, still the magnitude is going to be different. Now let's consider this particular reaction. A of A, B of B gives you is equilibrium with C of C, D of D, and all the reactant products are gases. Let's consider an example. Okay, we could have taken any example. Let's say we take this example. Now, equilibrium constant in terms of concentration would be Kc, which will be concentration of C raised to power C, D raised to power D, A raised to power A, B raised to power B. So this is what we call as Kc, the equilibrium constant in terms of concentration. Concentration is in molarity. Okay, this is molarity. Now let's talk about the mole fraction. Mole fraction of K is the C raised to power C, mole fraction of D raised to power D, mole fraction of A raised to power A, mole fraction of B raised to power B. Now here, mole fraction in itself is a dimensionless quantity. You don't need to take any standard here. What is partial pressure, Hansika? Partial pressure is the pressure exerted by the gas in a mixture of gases as if it is the only gas in the container. Hanshika, I would request you to see the session of gaseous state. We have already finished off the gaseous state, the states of matter. Please look at it. Partial pressure is given in Dalton's law of partial pressures. Okay. Welcome, Rahul Singh. Okay. Fine. And then we can use the concentration in terms of partial pressure. So it is partial pressure of C raised to power C, partial pressure of D raised to power D, partial pressure of A raised to power A, and partial pressure of B raised to power B. So it does not make a difference what unit of concentration we are talking about. You can use any unit of concentration and you can put it in the equilibrium equation. You are going to get the equilibrium constant. Okay. Rahul Singh, please don't spam. Now these values, these equilibrium constants can be converted from one to other. And but we need some constants which is required. Clear? Like we have PV is equal to nRT. So P is equal to N by V RT. Now N by V is concentration. Okay. N is number of moles and V is volume in decimeter cube. So N by V becomes mole divided by volume in decimeter cube, and this becomes molarity. Okay. So pressure becomes concentration into RT. Any doubts? Concentration into RT. So if I talk about PA, that will be equal to concentration of ART, molarity. And please remember this pressure is going to be in bar. Clear? In case of bar, we have to take the volume in decimeter cube. So partial pressure of B is equal to BRT, partial pressure of C is equal to CRT, partial pressure of D is equal to DRT. Now here Kp is equal to Pc raised to power C, Pd raised to power D, Pa raised to power A, Pb raised to power B. If we substitute these values from here, like here we substitute the values, this is going to be the expression, and finally we are going to end up with KCRT. Since we can take out RT common, C plus D minus A plus B. Okay. Remember, A, B, C, D, and so on are stoichiometric coefficient of gases. Please remember, for a reaction in which gases are not involved, Kp and Kc are same. वहां पे कोई इक्विलिब्रियम कांस्टेंट डिफरेंट नहीं आएंगे, वहां पे एक ही इक्विलिब्रियम कांस्टेंट हो जाएगा. ओके, clear? So only the stoichiometric coefficient of gases are considered. Reaction not involving any gas, Kc is equal to Kp is equal to K in terms of mole fraction. There is only one equilibrium constant. There are no two equilibrium constants. Is this clear? So that's what we have, the equilibrium constants. Okay. So we are going to talk about only delta Ng, but remember delta N also represents the change in the gaseous moles. Any kind of problems, anybody? So Kc is equal to Kp is equal to Kc RT raised to power delta N, or you can say Kp is equal to Kc into RT raised to power delta Ng. Is that clear? Clear? Now, talking about the Dalton's law of partial pressure. Partial pressure is equal to the mole fraction of the gas multiplied by the total pressure. Is it clear? So Pi is equal to mole fraction of I in the gaseous state multiplied by the total pressure of the gas. Is this clear? So if I want to get the mole fraction partial pressure of A, it will be mole fraction of A into P. Partial pressure of B is equal to mole fraction of B into P. Partial pressure of C is mole fraction of C into P, and partial pressure of D is equal to mole fraction of D into P. So what we had done with the partial pressure of we can calculate the partial pressure of A, B, C, and D from its mole fraction and the total pressure. So here we need total pressure at equilibrium. So conversion of Kp and K in terms of mole fraction, total pressure at equilibrium is required. Okay. So here we can convert each of the equilibrium constants into one from other. So what we can say is Kp is equal to Kc into RT raised to power delta Ng. That is the relation of Kp and Kc. Now to convert Kp and Kc, we need the temperature. If we know the temperature, we can convert one from other. And that's equal to K in terms of mole fraction into total pressure raised to power delta Ng. So if you want to convert partial pressure, the equilibrium constant in terms of partial pressure to the equilibrium constant in terms of mole fraction, then in that case you need the total pressure at equilibrium. So this is the conversion factor, you need to remember it. किसी को कोई दिक्कत? Great. Now let's talk about the degree of dissociation. What is the meaning of degree of dissociation? कुछ चीजें बहुत ध्यान से समझ लेना, बहुत ही ज्यादा ध्यान से समझ लेना. We are going to talk about the reaction in which the left hand side has only one reactant. Clear? It is also possible that it has more than one reactant, but the other reactant is present in a huge excess so that it's a solvent or it's a catalyst. So that also could be there. Is that clear? But we are only considering that the equilibrium equation has only one reactant. Okay. Now what we can consider is that that particular reactant, some fraction is consumed. Okay. Now the fraction of the reactant. Please remember, we are not talking about the moles of the reactant. We are not talking about the concentration of the reactant. We are not talking about the volume. We are not talking about the molarity. We are talking about the fraction. So the fraction of the reactant, and fraction of the reactant is a ratio. How much is consumed and how much was present. Okay. So the fraction of the reactant is dimensionless. Okay. Always between 0 and 1. Okay. Now the fraction of the reactant that has been consumed or converted into products at equilibrium. Degree of dissociation is not talked about कि इतना dissociate होता जा रहा है. We are not talking about rate of reaction. We are not talking about advancement. We are talking about the degree of dissociation. So at equilibrium कितना consume हो गया? कितना fraction consume हो गया? Clear? Am I clear what is degree of dissociation? So please remember, the degree of dissociation is always out of 1 or maybe 100 if you want to give it a percent. Okay. So degree of dissociation is always out of 1. Fraction of the reactant consumed. Clear? Degree of dissociation has nothing to do with the stoichiometric coefficients. It is always 1 minus degree of dissociation. Am I clear? Everybody clear with what the degree of dissociation is? Now we generally denote the degree of dissociation by alpha, but if you want to use any other symbol, you are most welcome to do it. You use the alpha, you use D, you use beta, A, B, C, X, your wish. But you need to tell, okay, I am taking the degree of dissociation as this. Tell it, declare it, and use it. Any confusions, anybody? So in terms of degree of dissociation, the amount of reactant present at equilibrium is 1 minus alpha. Is it clear? Now let's take a few examples. Let's say the equation is P gives you Q plus R. Now this is only one reactant. Okay. Now that reactant gets consumed and it gives us two products. It's not necessary it gives two products, it can give one product also. Now if 1 mole of P is consumed in the reaction, then 1 mole of Q and 1 mole of R are formed. The example of this kind could be PCl5 in equilibrium with PCl3 plus Cl2. This reaction is of the same kind. Is it clear that this reaction is of the same kind? So if 1 mole of P is consumed in the reaction, then 1 mole of Q and 1 mole of R are formed. If the degree of dissociation is alpha, it means alpha moles of P are consumed So alpha moles of Q and alpha moles of R will be formed. Okay. So I can say that if I have P in equilibrium with Q plus R, alpha moles of P are consumed. 1 moles of P are consumed तो 1 mole Q का बनता है. तो Q का alpha mole बन जाएगा. R का alpha mole बन जाएगा. Any confusions here? Those who have not liked the session, go ahead and like it. Any confusions, anybody? So now what we can even say is we have the initial concentration of P is C. Now for 1 mole, the concentration consumed is alpha. For C moles, it is the C alpha would be consumed. Clear? Just remember, this C is concentration of reactant, and that too initial concentration of the reactant. Just don't get confused. It's a very simple thing, but the student get confused in many things. Okay, so C is the initial concentration of the reactant. Clear? Your wish. You may call it P naught, no problems. Okay, so from 1 mole, alpha moles are consumed. Alpha moles of Q and alpha moles of R will be formed. If we have the C moles, then the entire equation is multiplied by C. So C is what? Initial concentration of P. That is reactant. Fine? हंसिका क्या समझ में नहीं आया बेटा, बोलो। इनिशियल कंसंट्रेशन ऑफ रिएक्टेंट, दैट इज सी। जो मर्जी ले लो, उसमें समझना थोड़ी ना है। सी समझना नहीं है, सी तो हमने इनिशियल कंसंट्रेशन लिया है। बिफोर द रिएक्शन, व्हेन वी स्टार्ट द रिएक्शन, वी हैव वन रिएक्टेंट। और क्या नहीं समझ में आया? और बोलो हंसिका, क्या समझ में नहीं आया? चलो आगे का देखते हैं, फिर और पता चल जाएगा। Now let's have this particular reaction. Now we have the stoichiometric coefficient P, Q, and R. Fine. Now remember, if I remove it, again it is going to be 1 minus alpha of P. Okay. See, from P moles of P, Q moles of Q, and R moles of R will be formed. Okay, I'll just take it a blank sheet. So if I have P of P is in equilibrium with Q of Q plus R of R, Hansika, yes, C1 minus alpha is fixed. C into 1 minus alpha is fixed. Okay. Now, for P moles of P, we get Q moles of Q and R moles of R. Okay. So if we have 1 mole of P, if we have 1 mole of P, we are talking about simple unitary method. Simple unitary method. If we have 1 mole of P, then we are going to get Q by P moles of Q. We are going to get Q by P moles of Q and R by P moles of R. Any confusions here? Any confusions here? Now, if it is alpha mole of P, unitary method, simple unitary method. We have some amount of something, we got it to 1, and then we get it to what we want. So if we have alpha moles of P, then in that case, it's going to be Q by P alpha moles of Q plus R by P alpha moles of R. Kind of confusion here? Those who have not liked the session, go ahead and like it. Okay. Now, if I multiply the entire equation by C, here we are talking about from 1 mole. Let us say we talk about C moles. P moles नहीं, अब C moles है, तो C से multiply हो जाएगा. तो if it is C alpha mole of P consumed, so it is going to give us Q by P C alpha moles of Q. समझ आ रहा है? आराम से करो, कोई जल्दबाजी नहीं है, कोई भागा दौड़ी नहीं है, आराम से करो. Plus R by P C alpha moles of R. Does it work? Think over. Anything to ask here? Note it down. Okay. So this is going to be the expression. So these ये जो सारी चीजें हैं ना these are the concentrations of all components. This is the concentration of the reactant. These are the concentration of the product at equilibrium. Any confusions? Now we have got the two expressions. It's not necessary that we have to have only two products. Product can be any number, but we are just taking an example of two products. There could be one product also, but it's easier to derive one product from two products. Okay. So let's find the equilibrium constant in degree of dissociations. Read this. Any confusions here? So here we have P upon Q. So it is going to be C into 1 minus alpha. This is going to be C alpha. This is going to be C alpha. Okay. These are the concentration of products. This is the concentration of the reactant. And we can get the Kc in terms of the concentrations. ये जो यहाँ पे लिखा हुआ है ना इसे बहुत ध्यान से समझ लो, बहुत ध्यान से समझ लो, because this is the part where we are talking about the degree of dissociation and we are talking about the equilibrium concentrations. And this part is going to be extremely important when we talk about ionic equilibrium. लोग आयनिक इक्विलिब्रियम में गलती करते हैं क्योंकि वो इस इक्वेशन में गलती करते हैं. Anything you would like to ask here? एनी कंफ्यूजन्स? ठीक है ना? अब सोचो, लेट्स कंसिडर द वॉल्यूम ऑफ द सिस्टम एज 1 decimeter cube. कोई फर्क नहीं पड़ता. But if we consider the volume as 1 decimeter cube, the concentration itself will become the number of moles. Okay? The concentration itself will become number of moles. Fine. And when it becomes, we can actually talk about the mole fraction. Mole fraction क्या होता है? Mole fraction of any component is equal to moles of the component divided by total moles in the system. Is it clear? So this is the mole of the reactant. These are the moles of the product. If we add them, we get the total moles in the system. Okay. C1 minus alpha is the reactant. C alpha is each product. Perfect. So we can easily get the mole fraction of P. That's the moles of P. And this one is total moles. देखो मैं एक एक चीज कई कई बार बता रहा हूं. अगर आप यहां पे ध्यान दे रहे हो तो आपको सब कुछ समझ में आ जाएगा. अगर आप बीच में सो गए हो तो आई कांट हेल्प इट. Yeah. In the same manner, we can find out the mole fraction of Q. Okay. And we can find the mole fraction of R. See one very important thing. Mole fraction does not have concentration term. सो मोल फ्रैक्शन के लिए आपको कंसंट्रेशन की जरूरत नहीं होती. आपको सिर्फ डिग्री ऑफ डिसोसिएशन चाहिए होता है. ओके. वी नीड ओनली डिग्री ऑफ डिसोसिएशन. ये बात समझ में आ रही है? Now, since we have got the mole fractions, we can find the equilibrium constant in terms of mole fraction. ये ध्यान से देखो, अगर आपने नोट किया है तो ये आराम से हो जाएगा. इज दैट क्लियर? अगर टेम्परेचर पता है तो आप केपी निकाल सकते हो केसी यूज करके. ठीक है. एंड इफ टोटल प्रेशर इज नोन, यू कैन फाइंड आउट द केपी. इज दिस क्लियर? ठीक है. तो यू कैन फाइंड आउट द केपी फ्रॉम कंसंट्रेशन और यू कैन फाइंड आउट द केपी फ्रॉम द इक्विलिब्रियम. ओके. बट इफ यू नो, अगर एक बात का ध्यान रखना, बड़ी मजेदार सी बात है, बहुत इंपॉर्टेंट थिंग. If instead of concentration I talk about initial partial pressure, then I directly get Kp. Okay. If instead of initial concentration, initial partial pressure of reactant is used. If instead of initial concentration, initial partial pressure of the reactant is used, then we directly get Kp. You can say Kp is equal to P alpha, and where P alpha is partial pressure of the reactant, okay, into P alpha divided by P1 minus alpha. Is this clear? So instead of concentration, we can use partial pressure also. And instead of Kc, we are going to get Kp directly. Then you can convert everything from Kp instead of Kc. Is this clear? Now, could we do it for this particular reaction? सेम थिंग जो आपने किया है वो इस रिएक्शन के लिए कर सकते हो. जरा इसके लिए कैलकुलेट करो, केसी निकाल दो फटाफट. This is going to be C into 1 minus alpha. Okay. This is going to be C into Q by P alpha and C into R by P alpha. These are the concentrations. आराम से कर लो, कोई जल्दी नहीं है, आराम से करो, ठीक से करो, समझ के करो, सॉल्व करो, पेन पेंसिल लेके करो, कॉपी में करो। कर रहे हो? ये समझ में आया? देखो हंसिका, आराम से बोल रहा हूं, बहुत आराम से बोल रहा हूं। अगर कोई चीज समझ में ना आए उसी समय पूछ लो, लास्ट में मत बोलना समझ में नहीं आया। फिर लास्ट में पूरा स्टार्टिंग से करवाना पड़ जाता, बहुत मुश्किल होती है। अभी बोलो क्या चीज समझ में नहीं आई। हाँ भाई, ये समझ में आया? ये वो टर्म्स हैं जो वेरिएबल्स में डिफिकल्ट हो जाती हैं, एक्चुअली इतना ही मुश्किल नहीं लगता। हंसी का मैंने स्टार्टिंग से इसलिए बोला था, आप फाइनल आंसर आने के बाद बोलती हो नहीं रहा। स्टार्टिंग से क्यों नहीं करते? यू वेट फॉर द फाइनल आंसर। मैंने आपका नाम भी लिया था, हंसिका बता दो ये समझ में आया? आप लास्ट में आंसर निकालने की कोशिश करते हो, बिल्कुल स्टार्टिंग से नहीं देखते हो। ये समझ में आया था हंसिका? हंसिका, ये समझ में आया था? अगर आप बाहर चाय पीने चले जाओ, चलो आगे अब देख लेते, अब देख ले, अब आ जाएगा। फिर घूमने निकल जाओ, फिर पानी पीने बैठ जाओ, तो बेटा ऐसे तो नहीं होगा। और नहीं, हम तो पढ़ेंगे, देखेंगे, देख रहे हैं, देख रहे हैं, देख रहे हैं। लिखो नहीं, नहीं होगा। और मायूख, अब उस दिन की डांट के बाद आपको पेन पेपर में क्वेश्चन करने पर समझ में भी आ रहा है। एंड नाउ अब हंसिका की बारी है। आई बिलीव इसलिए मेरी क्लास में बस 7 बच्चे हैं, क्योंकि उन्हें काम करना पड़ता है। ओके हंसिका, ये समझ में आया? अब ये समझ में आया? और अगर ये समझ में आ गया है तो यहां पे तो सिर्फ सब्स्टिट्यूट करना है। यू जस्ट हैव टू सब्स्टिट्यूट। और करना क्या है? लिख के करो हंसिका, हंसिका लिख के करो, आ जाएगा आंसर। लिख के स्टूडेंट नहीं करते, बदनाम इक्विलिब्रियम होता है। या टीचर होता है। टीचर ने नहीं पढ़ाया हमें, टीचर को नहीं आता कुछ, हम तो बहुत इंटेलिजेंट है ना। टीचर को ऐसे पढ़ाना चाहिए कि बच्चा आंख बंद करके सो जाए फिर भी उसको समझ में आ जाए, ऐसे पढ़ाओ। कोई बात नहीं, वो भी कर रहा हूं, सोते सोते पढ़ना तुम, वो भी कर रहा हूं, मिल जाएगा तुम्हें 2 दिन के अंदर। अब हुआ आंसी का ये वाला क्वेश्चन, देखो मैंने कुछ नहीं किया, आई डेंट टेल यू एनीथिंग, आई जस्ट आस्क यू टू रीड इट अगेन। Now again you consider the volume as 1 decimeter cube. The concentration itself will become number of moles. और उसके बाद ये आ गए total number of moles. बस ऐड कर दिया सबको। अंशी का बेटा नेटवर्क इश्यू तो पता नहीं कहां कहां चल रहा है, मेरा भी नेटवर्क इश्यू चल रहा है, पता नहीं क्या। स्टार्टिंग में while starting the class there was a network issue, there was YouTube issue। क्लियर? So that is what we have as mole fraction, but complicated equations हैं, कोई बात नहीं। मोल फ्रैक्शन ऑफ पी निकाल लो, मोल फ्रैक्शन ऑफ क्यू निकाल लो, मोल फ्रैक्शन ऑफ आर निकाल लो। ठीक है, रहने दो। I believe we have already discussed about what is vapor density। क्वेश्चंस में डिस्कस किया था वेपर डेंसिटी क्या होता है। Vapor density is the density of the vapor of a substance with respect to the density of a standard gas। Okay, most often the standard gas is 2, that is hydrogen, so that is why vapor density becomes molar mass by 2। ये पढ़ लिया? अब एक ध्यान से समझो, if a gas dissociates, then at equilibrium the total number of moles will be more than the initial number of moles, the observed vapor density would be lower than the theoretical value। Okay, सिंपल सी बात है. If a gas dissociates to NQ gases, then it's going to be 1 minus alpha. This is going to be N alpha. Now, the observed vapor density will be equal to that vapor density divided by 1 minus alpha plus N alpha. That is the relation of the observed vapor density to the actual vapor density. It could be the relation with the molar mass as well. खतरनाक है ये. चलो, अब हम एक्चुअल एग्जांपल्स की बात करते हैं. थक तो नहीं गए? थक गए हो क्या? तो चलिए इसके साथ कीजिए. गिव मी द केपी, केसी एंड के इन टर्म्स ऑफ मोल फ्रैक्शन फॉर दिस पर्टिकुलर रिएक्शन. कोई प्रॉब्लम इसमें? ये एग्जांपल हम ऑलरेडी कर चुके हैं. कोई कंफ्यूजन इसमें? अगेन सेम थिंग, सारी चीजें. मोल फ्रैक्शंस कर रहे हो? Absolutely same. The first example again. The only thing is हमने PCl3, PCl5 giving you PCl3 plus Cl2 लिख दिया है. कोई दिक्कत? Great. Hanshika also has no problem now. हो गया? चलो इस रिएक्शन के लिए करो. Find the Kc for this reaction. Remember, Kc is equal to the concentration of NO2 raised to power 2 divided by the concentration of N2O4. बनाओ इसके लिए. Yes. कोई confusion? Mayuk got it. Everybody else got it? Got it, everybody? फिर से वही बात. And we can find out the mole fraction in terms of mole fraction also. Try करो. K in terms of mole fraction. मुझे पता है मेहनत लग रही है, मुझे पता है इरिटेट हो रहे हो, मुझे पता है बहुत मुश्किल लग रहा है, लेकिन जैसे जैसे करते जाओगे होता जाएगा और इक्विलिब्रियम फिर टिप्स पे आ जाएगा. एक दिन की बात है ना, कर लो एक दिन मेहनत. एंड इक्विलिब्रियम इज समथिंग लाइक गले का फंदा. इजी. ग्रेट. तो चलिए ये वाला करो, इसका करो. फाइंड द केसी. मजा आ रहा है या ऐसी तैसी हो रही है? ये इक्वेशन लिखना भूल मत जाना, वरना इतनी बड़ी सिली मिस्टेक करोगे और फिर समझ में भी नहीं आएगा क्या हो गया. कोई शॉर्टकट मत मार देना इक्विलिब्रियम चैप्टर में, कोई भी शॉर्टकट नहीं. इसका निकालो केसी। हाँ जी, इसका क्या आया? केसी आ गया। तीर्थराज मुखर्जी, मायूक सेन गुप्ता। Wow, that's the thing, that's the spirit. You have got it right. Both तीर्थराज and मायूक have got it right. अच्छा लग रहा है। अचीवमेंट। अब मोल फ्रैक्शन के टर्म्स में निकाल लें। अब इसका मोल फ्रैक्शन के टर्म्स में निकाल लो। क्लियर? द फाइनल आंसर इज दिस। चलो इसके लिए करके दिखाओ। एंड देन वी आर गोइंग टू डू अ फ्यू क्वेश्चंस। Do this one. And whoever has not liked the session, go ahead and like it. वाह, मायूक, क्या बात है. तीर्थराज, आंसर नहीं आया आपका, क्या बात है? व्हाट अबाउट द अदर्स? सामने आंसर लिखा हुआ है, फिर भी सॉल्व नहीं कर रहे हो. ओके. यस. तीर्थराज मुझे कह रहे हैं और दीजिए बेटा, अभी आ रहे हैं और. तुम्हें क्या लगता है, नहीं है और बहुत सारे. सो हियर इज द रिलेशन विद द मोल फ्रैक्शन. पहले मोल फ्रैक्शन निकाल दो ना तीर्थराज, और दीजिए तो. इसी क्वेश्चन का मोल फ्रैक्शन में निकाल दो. एक तो 30 सेकेंड पीछे चल रहा है ना. आ गया? Solve this question. Yes, alpha is 0.25. Now this is another question, and this is the final question. Join our Telegram channel for YouTube classes, PDFs, t.me/NEET Elixir, and download the app. और कल सुबह हम एनसीईआरटी पढ़ते हैं, ठीक है? केमिकल इक्विलिब्रियम की। हर्ष द्विवेदी, वेलकम। और जिसने भी लाइक नहीं किया जल्दी से लाइक कर दो। Unacademy.com/Anup is my page on Unacademy where you need to follow me and subscribe to NEET Elixir by Unacademy. ठीक है? थैंक यू। मिलते हैं कल सुबह 10 बजे। यस, मायूक खत्म। केमिकल इक्विलिब्रियम की एनसीईआरटी पढ़ो, and we are going to solve the NCERT tomorrow morning at 10 a.m. Fine? Bye bye. गुड नाइट। आज शाम को हमारी क्लास नहीं है, स्पेशल क्लास कल रखेंगे, ठीक है ना?